If you don't know how to properly design the last layer of the neural network, your model may not work, and you won't be able to solve your machine learning problem properly using neural networks. Hello everyone, my name is Amin Omidvar, and in this video, I'm going to show you how to design the last layer of a neural network model for each specific machine learning task. If your data has labels, you are probably going to solve one of these supervised machine learning tasks. These supervised tasks are binary classification, multiclass classification, multilevel classification, regression, and ordinal regression. It is important to know which one of these categories is related to your machine learning task, since the activation function and the number of neurons in the last layer may be different based on what kind of machine learning problems you are going to solve. An input layer of a neural network model always depends on the input features. Generally, the number of neurons in an input layer is equal to the number of input features that you have in your training dataset. The number of hidden layers and the number of neurons in each hidden layer are hyperparameters of your model, and you are free to choose whatever values that you want. Basically, you will use hyperparameter tuning techniques to choose the number of hidden layers along with the number of neurons in each of them in a way that the trained model can have its highest accuracy on the validation dataset. Choosing an activation function for each hidden layer is another hyperparameter too. Almost most of the time, we choose the ReLU function, which has better performance in comparison with other activation functions such as sigmoid, tanh, and linear functions. But for the output layer, the number of neurons in the output layer depends on the number of classes that you have in your dataset. But the configuration and the type of activation function that you choose depends on which supervised machine learning task you are going to solve. In this video, I will introduce each of these machine learning tasks briefly, and also I will show you guys how to design the last layer of a neural network model according to each machine learning task. Binary classification is a task of classifying the elements of a set into two groups. For example, we have a dataset containing characteristics of patients, and we are going to train a model by getting those characteristics as input data, and the model will predict whether a patient needs an eyeglass or not. So, in the output of the model, we should have two states in order to determine whether an eyeglass should be prescribed or not. One way to implement our neural network model is by having one neuron in the output layer. As I said in the previous slide, the number of neurons in the input layer only depends on the number of input features, and the number of hidden layers and also the number of neurons in each hidden layer are the hyperparameters of our model, and you are free to choose whatever values that you want. So when we choose one neuron for the output layer, it is better to have a sigmoid for its activation function. Then if the output value of the activation function is above 0.5, we label it by yes. That means an eyeglass should be prescribed. But if it is below 0.5, it is no, and in this case, there is no need for an eyeglass. Here we can see the formula of the sigmoid function. Z is the input to the activation function, which is calculated by the neuron. Then the sigmoid function will convert Z to the value between 0 and 1. And here we can see the image of the sigmoid function. As we can see, for any range of input values, the output will be always in the range of 0 to 1. If the value is above 0.5, it means the neuron is activated. This is the most common way to use a neural network for a binary classification task. There is another way to design a neural network for the binary classification task as well, which I will show you in the upcoming slide. Instead of having just one neuron in the output layer, we can build our neural network by considering two neurons in the output layer. In this case, if the output of the first neuron, which means P1, is greater than P2, then we assign the first label, which is no eyeglass is needed. And if P2 is greater than P1, then we assign the label yes, which means an eyeglass should be prescribed. The other difference between these two structures is that we use softmax instead of using sigmoid for the activation function of the last layer. For each neuron, the softmax function will calculate e power of z, then divide it by the output of the neurons, which in our case, we just have two neurons. Then the value of P1 and P2 will be calculated according to these two formulas. Basically, softmax function will convert the output of the two neurons into a probability distribution in a way that the sum of the output of all neurons will be equal to 1. Also, the output of each neuron will be in the range of 0 to 1. But which one of these approaches is better? Using one neuron or two neurons? In practice, there is no difference between these two approaches in terms of the accuracy of the model. So in the end, the result will be the same. But by using one neuron, you will have fewer parameters to learn, so the size of the model will be smaller. The most common supervised machine learning task is a multi-class classification. Basically, here we have more than two classes, and the task is to assign only one class exclusively to each instance in our dataset. For example, we have a dataset containing some information regarding patients, such as their age, whether they have astigmatism or not, tear production rate, and the task is to determine what kind of lenses they need. We have three different lenses, which are non, soft, and hard. So the number of the classes in this particular example is 3. Because the number of classes is more than 2, and we should prescribe only one lens for each patient, so our task is a multi-class classification problem. Basically, if our task is a multi-class classification, the number of output nodes should be always equal to the number of classes, which for this example they should be 3. The reason is that we consider one neuron exclusively for each class. Then we look at the output of all neurons in the output layer, and we predict a class that the output of its neuron has the highest amount of value among the other neurons. Also, we use softmax for the activation function of the last layer to convert the outputs of the last layer into a probability distribution. The way we design the last layer of a neural network model for a multi-class classification task is similar to the way we did for a binary classification when we had two neurons in the output layer. Similar to a multi-class classification task, in a multi-level classification task, we have more than two classes. But the difference between these two tasks is that in the multi-level classification task, more than one class can be assigned to each instance in our dataset. Basically, in the multi-level classification task, there is no constraint on how many of the classes the instance can be assigned to. Here we have a simple example of a multi-level classification problem. We have a corpus of news articles, and the task is to find out the topics of each news article. The blue part of the table contains features of the news articles that we use them as the input to the neural network model. Basically, these features are a simple bag of word representations of the news articles. And the red part contains our classes, which are technology, business, and politics. We can see that the first news article is assigned to the politics and the second one is assigned to the technology. But the third one is assigned to both technology and business classes. Some news articles may be related to two or more than two topics. So, in contrast to the multi-class classification problem, which only one class could be assigned to each instance, in multi-level classification, we can see some instances can be assigned to more than one class. Another famous example regarding the multi-level classification problem is an object detection task, in which there are multiple objects in an image and the task is to label what kind of objects exist in the image. In the left image, we just have a cat, so we assign a cat label to this image. But in the right image, we have both a cat and a lion, which we assign these two labels to this image. For designing a neural network model for the multi-level classification task, as always, we set the number of input neurons equal to the number of our input features. And similar to what we did for a multi-class classification problem, the number of neurons in the output layer is equal to the number of classes, which in this case is 3. But the difference is we use the sigmoid rather than using the softmax for the activation function of the last layer. The reason is, for some instances in our training dataset, we have more than one label. So we want our neural network can generate more than one output for some instances that should be assigned to more than one class. The reason that we cannot use the softmax function for the multi-level classification task is if we use softmax, then the output of the neurons in the last layer will be all interrelated to each other because they will form a probability distribution. That means the sum of the outputs will be always equal to 1. Thus, if we are using a softmax function, when the probability of one class is increased, the probabilities of at least one of the other classes must be decreased by an equivalent amount. In contrast, the outputs of the nodes using a softmax function are independent of each other and are not constrained to sum to 1. That means sigmoid look at each neuron's output value separately. So when we are using a sigmoid activation function, each output neuron can tell us whether an instance belongs to its specific class or not without having any effects on the output of other neurons. Regression is a subfield of a supervised machine learning task. The main difference between a classification task and a regression task is that the output variable in the regression is numerical or continuous, while that for the classification is categorical or discrete. In regression, sometimes we call input features as independent values and the output as dependent value. Here we can see a very simple example of a regression problem. Imagine we have some tweets and the task is to predict how many likes each tweet will receive from the audiences. The number of likes is a positive numeric value which starts from 0. It is possible to have more than one output or dependent values in a regression task. If that happens, our task will be called a multivariate multiple regression problem, which I will talk about it in the next slide. But for now, let's assume we have just one output or one dependent value, and we are going to design a neural network model to predict how many likes each tweet will receive. As always, the number of input neurons is equal to the number of input features. In the output, if we just have one output or one dependent variable, we will consider only one output neuron. And we use a linear activation function for that output neuron. Basically, when we say we are using a linear activation function, it is equivalent to say that we don't have any activation functions for that neuron, because whatever neuron calculates from its inputs, it will be considered as its output without any modifications to that. If we have two or more targets or dependent variables, then our task is a multivariate regression problem. In this case, we will consider one neuron for each independent variable in our output layer. So the number of output neurons should be equal to the number of the dependent variables, which in our case, we should have two neurons in our output layer. And same as before, we choose a linear function for the activation functions of all neurons in our output layer. One important thing here is that if we have just one target variable in our regression model, we don't need to normalize the output variable. But if you have two or more targets and their scale is different, like the number of likes is between 0 to 1 million and the number of comments is between 0 to 10,000, then it is so important to normalize them to make their scale the same. Otherwise, if we do not make the scale of our target variables the same, then our model will put most of its effort to learn the number of likes rather than learning to predict the number of comments. But by normalizing our target variables, both target variables will have equal importance to the model. You may be thinking, why not just run separate regressions for each dependent variable? I mean, having one neural network model to predict the number of likes and another neural network model for predicting the number of comments. That's actually a good idea. We can do that and consider a separate neural network model for each target variable. If we use this approach, then there is no need to normalize the target variables anymore. Ordinal regression is an important type of supervised machine learning task which has properties of both classification and regression tasks. Unfortunately, most data scientists make a mistake and consider an ordinal regression task as a multiclass classification task. The reason is that, like a multiclass classification task, the learning task of ordinal regression is to assign instances into a set of finite categories. But the difference between an ordinal regression task and a multiclass classification task is that in the ordinal regression, these finite categories are ordered. For example, we have a dataset of students' essays that were marked by teachers using A, B, C, D, and E grades. So we have 5 categories for grading, which we should assign each essay to one of them. But these categories are ordered, which A is the best one, then B is the second best, and so forth. Imagine that we train 2 neural network models which can mark essays automatically for us. For example, we have an essay which its real grade should be B. The left neural network model predicted a grade A and the second one predicted a grade E. In terms of classification's point of view, both models failed to give us the correct answer. But we prefer the answer of the left model than the right one, since the left model gave us a closer grade to the real one, which B is closer to A than to E. So the goal is to train our neural network model in a way that it not only learns how to assign each instance to its category correctly, but also learns the existing order between the categories. By learning the existing order between the categories, the neural network model will give us at least a close prediction to the real one, in a case that it cannot predict the correct label. So to wrap it up, the ordinal regression is different from the multiclass classification since the classes are ordered. Also, the ordinal regression task is different from a regression task since in the ordinal regression, the output is discrete and finite. You now know what is an ordinal regression task and how it differs from multiclass classification and regression tasks. Now let's see how we can design a neural network model for ordinal regression tasks. In classification tasks, for the output classes, we usually put 1 for the correct answer and 0 for the others, which we call it a one-hot encoding representation. But in the ordinal regression task, we put 1 for all the categories that are lower than the correct category and 0 for those that are higher. For example, in the original data, the grade of the first essay is C. So we have 1 in the C column, but 0 for the other columns. We will change labels according to the bottom table, which all the grades that are lower than C will be 1 and the others will be 0. When we train a neural network model based on the modified labeling approach, the model can learn the existing ordering between the categories. For the prediction part, we always consider the highest rank category that contains 1. That for the first essay, it should be C. Same as the multi-class classification task, the number of neurons in the last layer is equal to the number of the categories. But instead of using a softmax, we use a sigmoid for the activation function of the last layer. This approach was proposed by Cheng and his co-authors in the following article. I hope you guys enjoyed this video. If you have any questions, don't forget to ask them in the comment section. And please like the video if you find it useful. I wish you guys all the best.